say, but how do you design the outer body layer? Using an ECAD software now. Nobody manually goes and takes a hammer and starts hitting, right? It's done robotically now. Who said robot is mechanical engineer? What do they know about robots? It's all ours. Okay, good morning. This is the, which day it is? I have lost count of how many days I have been here. Is it the 5th day? Okay. So for those of you who are joining for the first time, things might look a bit shaky, but don't worry, it will not be too difficult. So for those of you who were yesterday, we looked at mechanical sensors. Essentially, we wanted to make mechanical sensor on top of our chip. Our idea initially was to measure mass. In the end, I don't like mechanically, they're very complex. So the idea, if we can define mechanical systems as electrical system. So just quickly, this is what we did yesterday. We looked at a mass spring damp system. So this is a high school maths for, again, you guys. Take a spring, attach a mass, pull it, it will come and up and down, right? And then there is a damper. And the equations we realized were fairly simple equations. Where's my stick? That fairly simple equation, we say Newton's law is, that's only mechanical engineering I know, Newton's second law of motion. Move away. My apologies. Okay. That way he can focus at one place. He's already complaining, I'm moving. Am I moving too much? Okay. Okay. So we said the Newton's law of motion is mass into acceleration, so mx second derivative. And the restoring force, if analysis to figure out, okay, that's a second order differential equation, we can solve it, we can find some, if you excite the force with sinusoidal force, the response will also be sinusoidal. If I pull it with a sinusoidal force, the mass spring will also move with sinusoidal force. The other thing which we did was we looked at the frequency response, and that looks like this. If it has got high Q, it has got a sharp frequency response, low Q, low frequency response. And then we said we can use it as a mass sensor. The idea of using it as a mass sensor was my resonance frequency of the system is square root of K M, where K is the stiffness, M is the mass. So if I change the mass by a small amount, mass plus delta M, I can do a Taylor series expansion of this. Root over K over M comes out, 1 minus delta M by 2M comes out. Which means my resonance frequency, if my mass changes, my resonance frequency changes. If my inherent and the change in resonance frequency is change in mass divided by my actual mass. So if I make a resonator which is very low in mass, my resonance frequency change, then I can measure even lower mass changes, which is natural, right? If my weight is lower, I can measure low weight. Good. The other thing which we saw was we tried making large resonators of other things. Now the way our mechanical engineering colleagues or even we try to design these resonators, these beam resonators or spring resonators, is by doing finite element simulation. Essentially what you do is you divide the whole structure into really tiny small masses, and then you apply the same mass spring equation in each one of them. Now you can imagine, even if it's a 100 micrometer structure and dividing it 1 nanometer structure each, the simulation time will be long. So multiphysics simulation, which tries to look at either finite element or finite time, they're accurate but time consuming. The way what we would like to do that is what we call as scientists should never marry. Their wives have a unique tendency to call when you are giving lectures, or their husbands. This goes both ways. The way we said is, rather than thinking of it as a continuous system, why don't we think as a lumped mass system? By lumped mass system, okay, there's a beam, we assume it's a point mass. There's a mass and there's spring constant. That these two are separate from one another. Okay. Now this is not a very accurate analysis. So let's say this is a beam. The mass is not just here. Actually, rather, there is no mass here. Right? The mass is distributed. The stiffness is also distributed. If I move it up and down, that's not uniform. That's not one place. So if I simulate it from each point, it will take a lot of time and energy. But if I'm able to say the entire mass is just here, 1 point mass, and this whole thing is just a spring, that will be easier for me to simulate this system. Right? So essentially what we do is we convert this continuous system into discrete elements. And then the idea is that these discrete elements talk to one another discretely. And we now don't write continuous equations, we write terminal equations. Okay? So the whole system, rather than being a continuous mode operation, becomes a simple mass spring system. We also don't consider temporal analysis anymore. So we do not look at how slow or fast it will move, because we have already approximated it as 1 point. Good. So the other thing which we would like to do is, we know electrical engineering equations or electronic engineering equations. So if we can transform this beam into an electronic engineering counterpart, life would be very easy for us. Now let's start with how to transform this into an electrical engineering circuit. Now there are few things which are happening here. So in electrical engineering, what are the fundamental devices we have? Resistance is there, capacitance, inductance. Let's not go transistor, that's very hard. Simple, right? By now the other people would have known I don't do hard things. So those are three fundamental device elements. If we get time, in the afternoon I will also teach you about the fourth fundamental device element. Have you guys come across memristor? Have you heard the term? Some of you? So in 1970s, Leon Chua in US predicted that this theory of resistance, inductance, capacitance seems incomplete. So think of, I will see the incompleteness later as to how physically it's incomplete. So he said there has to be a fourth fundamental element, which was predicted to be memristor. We'll see how it is fourth fundamental element, and we'll see it using first order physics analysis. But for the time being, resistance, inductance, capacitance, we know that. What else do we have? So these are static quantities. There's something which moves. So we have current. Current is moving through a particle. And then we have voltage, which is applied across something. So whatever resistance, voltage is applied across it, current moves through it. Okay? Good. Now this gives us an interesting thought process. If we can think these as terminal devices, can we think of them as two-port devices? They have two terminals. Right? If we transform each one of these into two terminal devices, then most of our devices are also two terminal devices. Okay? Transistors are three terminal. So most of ours are, so let's think what's happening here. What does the damper do? It stops us from moving, right? It is dissipating energy. So actual energy goes into moving the system. Whatever energy goes in dissipation, damper goes out as heat, goes out. Now there is something in electrical engineering which also tries to stop something else from moving. So if a moving material is current, what stops current from moving? Resistance, right? Resistance also does the same thing. It also dissipates energy. So one can think an equivalent of damper would be resistance. Okay. Now what does my mass do? It tries not to move. By given a choice, mass will not move. Okay. So now I've replaced this with a resistance, which was the easy job. But now I have a mass and I have a spring. What does spring do to the system? It gives the force to pull it up and down, or rather it stores energy in one cycle and then gives energy on the other cycle. What element does that to us? A capacitance? Well done, right? So if we think this in those lines, there are another way of thinking. So one direction I'm thinking. Now if you're like me, you are like, that's resistance, that's capacitance, this has to be the third one. Right? We can argue how it becomes an inductance, but if nothing else, it will be the third one. Okay? Good. But that's not the only way of thinking of this thing. So at this point, there's another thing here, the force. I'm applying a force. What is force here? Because I have left with two other quantities, current and voltage. So which one of them is the force? So let's take one step back here. So I said that is resistance, right? What's the relationship of the moving quantity, current, and resistance? Voltage is equal to IR. That much we know, right? Ohm's law we know. Good. What is the relationship in a damper? What does a damper do? Yes, but what's the equation of a damper? B times x dot. If B is my damping coefficient, it damps based on your velocity, right? And that's an interesting thing. Basically, what I'm saying, if I try to look similarity between the equation, I have B is equal to IR, and here I have got whatever is equal to B times velocity. Okay? So from this, and I said B and R are similar. So from this argument, velocity is my current. Not making sense? Okay, let's try it again. And I should have taken a whiteboard. This is why I like whiteboards. These are very difficult to understand. But think of it this way. Okay. Let's go back to the damper. Okay. First page. Here. That part of the equation comes from the spring. This part of the equation comes from the damper. What is this equation? This is B times x dot. X dot is velocity, right? It's not displacement, it's velocity. Good. Now, if we look in electrical coefficient, we said damper is resistance. We all agreed on that. That's not the only way, but let's start with one. Resistance equation is voltage is equal to current times R. Right? So if R becomes B, then by that logic current should become x dot. Right? So my velocity in the system is my current. Now this is very interesting because in mechanical world, people were looking at displacement. We on the other hand look at voltage and current. So if I do similarity, my current becomes, now what does happen to my voltage? So what is left in all of this? Force, applied force, right? This time velocity is force, so I can argue force is my voltage. Good. Now, there's another way of looking at this. Rather than arguing force as voltage, I could argue velocity to be voltage. And then I can go back and looking at the same energy relationship there. It's an indirect relationship rather than a direct one. So direct one was this. We take force to be voltage. We take energy to be the potential energy in. Remember, where is energy coming from in mass spring system? It's just the stiffness. Right? So now our energy is the potential energy in capacitance. My springs become capacitance and my mass becomes inductor. Had we gone in that route, our springs would have become inductors. Okay? Now there are a few more equations which we need to see, because we have only equated the elements. We have not equated all the equations. Now we have some equations in electrical engineering. What are our fundamental equations? Kirchhoff current law, Kirchhoff voltage law. We know that thing, right? We know Ohm's law. Those equations don't exist in mechanical engineering. So let's try to find equations how we can relate these two. There are a few more things which happen there. So we have things called displacement, x of t. We have velocity, dx by dt. Effort could be force. We also have something called momentum. What is momentum? Mass into velocity. Good. And then we have net power, okay, which is velocity into whatever is the effort you are applying. So let's start with how do we divide. Now we are looking at only at electrical components right now, but we'll find equivalent from fluid dynamics, from thermal engineering. Remember, we have got tons of different sensors. So we're going to translate everything. So we said, okay, our effort becomes voltage. Our flow, whatever is moving, is current. So what was displacement now? We forgot to talk about displacement. Current is velocity. No. What is moving? Charge. Charge is moving as current, right? So earlier we said in mechanical world, displacement is x, velocity is x dot. When x dot is current, x becomes charge, right? So charge is fundamental for us. We don't have an equivalent of momentum in, well, we have, but we don't use it frequently, okay? Our resistance is resistance, capacitance, inductance. What is our node law? Kirchhoff current law is our node law. Every current at a node B is 0. Sum total of all current in a node is 0. Now voltage, mesh law is the voltage law, right? If you go into a mesh, the sum total of all the voltages will become 0. Let's see the equivalent in mechanical world. So without said, effort becomes force, flow is velocity, displacement is displacement in this case, and we have got momentum now. And then we said our resistance becomes a damper, capacitance becomes spring. The inertians, things which is not moving, is mass. Now mesh law, Kirchhoff voltage law, what does the voltage law does? It looks at voltage in each unit, right? That kind of becomes Newton's second law here. What does the Newton's second law say? Mass into acceleration is force applied. I'm sure this one is asking me to sell something, or I really like taking these phone calls when they try to sell you something or ask you to, become or vote for something. Anyway, let's get back. So mass, which is one is mass for me? Inductance into, or think of it this way, forget about inductance. So it's, what's my velocity here? Velocity is I, acceleration will be di by dt, L di by dt is L di by dt is voltage. So that kind of looks from here, voltage is equal to my mass times acceleration. Okay? Let's look at it in the other terms. What's the voltage here? Resistance times current. Damper times velocity is the force. Newton's second law, right? From if we just have fixed velocity, then the friction dampening times velocity is the force. And similarly you can do from this equation as well, from spring equation as well. So Newton's second law becomes my mesh law. The current law is a little bit tricky. I mean, there's continuity of space. You're basically saying the space is continuous. Okay. Now, how many have you done fluid dynamics as part of your undergraduate? Have they taught fluids? One person? We generally hate fluid dynamics. I mean, I hate it from the bottom. I hated anything with mechanics. My initial question was, why am I learning mechanics? Transistors will stand, computers will not fall down. But much later, when I was doing my postdoc, I realized I should have given more attention to those subjects. So let's look at fluid. Now, what's equivalent to effort in fluid? It's the pressure at which you send a fluid. Okay? Now, flow will be at what rate my liquid is flowing. Okay? Agreed? Momentum is pressure, momentum, let's forget. Now, all of these things I have defined in terms of fluidic resistance. There is a resistance for it. It has got viscosity in other terms, but I can define it as fluidic resistance, a fluidic capacitance, and some inertance to move. Now, the interesting thing is from current law. In fluid world, we have got law of conservation of mass. Mass does not change, right? Overall, the total mass in a system remains constant. And that's similar to our current law. We're not gaining or increasing current. It always remains the same. Okay? So even if there's a fluidic system, I can convert the fluidic system into my resistance capacity by looking at these terms. Maybe fluidic resistance is not well defined, but I can count it as there is a rate of flow that is defined. How is flow changing with time? Okay? Let's look at the thermal system now. Now, temperature difference will be my dt now. Heat flows when there is a temperature difference between two things. Voltage is potential difference, right? So, if potential is temperature, temperature difference is my potential difference. Heat flow becomes my flow, heat is moving. Okay? Heat now becomes my charge, my displacement material, which was moving. Okay? And then we can define a thermal resistance, a heat capacity. We do have the law of conservation of heat. So that becomes equivalent to my Kirchhoff current law. And we have temperature is relative, which becomes, because we don't have an absolute temperature. Temperature is related to something else. Okay, we have an absolute temperature, but generally we measure it relative to something else. So this is interesting. We have now found an equivalent material or equivalent electrical component to mechanical, thermal, and fluid things. So when you guys go home, you can say all that they study in mechanical engineering, we study in second year, first semester. That's when we studied these two, right? Those guys study it for 4 years. They will kill you, but it's no harm in stating that sentence. Okay. Now let's try to transform a particular circuit. So now we have got mechanical power, electrical power, and we have got all of these things there. Voltages, resistance. So we did all of this. Can we now write an equivalent circuit to this one? What will be that circuit be? Right. We have also given you the components. We have got springs, which will be the capacitor. Actually, let me have a look. So resistance we said will be B. Okay, that was easy. Now what happens to spring? Now it is capacitance, but what's the relationship between these two? So let's think of it this way. What's the force in a capacitor, or what's the force in a spring? Kx. Right? Now x is for us x dot velocity. So x is charge. What's the relationship between charge and voltage? No, dq by dt is current. We're just looking at, so charge is voltage times capacitance. Q is equal to Vc. Right? Agreed? Not agreed? I might be wrong. Correct me if I'm wrong. No? So, if we now equate these two relationship, now voltage is my flow. So voltage is equal to Q by C. In this case, force is equal to Kx. So Kx becomes equivalent to Q by C, which means K becomes 1 over C, or C becomes 1 over K. Right? Okay. And the last but least is the mass equation. So if I look at voltage is L di by dt or L dq d by dt square. In mechanical world, force is equal to mass times acceleration. I get m d2x by dt. We have said x is equivalent to charge. Hence, mass and inductance could have the same value and the circuit will become equivalent. Okay. So now I have got what will be the inductor, what will be the resistance, what will be the capacitor. So inductor and resistor will have the equivalent value of mass and spring constant. The capacitance will be 1 over K. If I think on these terms, I can now equate this system to this. Capacitance, inductance, resistance, force applied. Current is measuring the displacement which I have. Agreed?
How force is applied?
So in this case, force pulls the mass here, right? But the force gets applied on all of these things, isn't it? When you're pulling it, the force is also working on the spring constant and damper. If this looks a bit of wizardy, let's look at the equations. We saw that equations. That was a second order differential equation. All of you guys can write the equation of current here, which will be, what will be the current flowing here? Let's write it, because we're trying to find equivalence here. Okay. And remember, the other side, my x was charge. So think of, or better write the charge equation if you can write the charge equation. So voltage is equal to, no. So write the current equation and then we'll replace I with dq by dt. So if So if you guys would have done, it's a very simple circuit, you would have done F is equal to, what will be the term here? C dV by dt is current, but I'm looking at loop, right? So this is F, that's my voltage. That has to be equal to the voltage drop here plus voltage drop here plus voltage drop here. So what's the voltage drop here? So current is C dV dt. So voltage is integral of I dt, right? 1 over C I dt. Yes? No? Agreed? What's the drop here? L di dt. And what's the drop here? Ri. Simple as that. Okay. Now I is dq by dt. In your equation, let's replace I with dq by dt. And what's the equation you guys get? It's a second order differential equation in charge. So you should have got dq m dq double dot or mq double dot plus bq dot plus 1 over cq is equal to force. It's the same equation as we had there. So have we got something like this? I hope I am correct. Now, in electrical engineering, are you all with me? Should I proceed or would you like to wait? Okay, we'll give them a few more minutes. Don't worry about copying, you will get the slides. It's not worth copying the whole thing. Now, in electrical engineering, we define this complex quantity called impedance. Right? This is, what's the impedance of a capacitor? I hope you guys know impedance of a capacitance and impedance of an inductance. J omega L 1 over J omega C. And we are the people who use J for complex number. We annoyed the mathematician quite a lot because they use I. For complex number they use I, right? We had already used I for current. So we had to use something else. So we are the ones who annoy them. Now, this equation then now allows us to define a complex mechanical impedance. So essentially we have converted that circuit into this. We can say all of this is a mechanical impedance of the circuit. Okay? Now as an exercise, would you guys like to transform that into its electrical equivalent? So I'm giving you a simple circuit to start with. And well, you need motivation. Where do we use this thing? Let's give you the motivation thing where we can use it, and then maybe you'll be interested in converting this into an electrical. So that is a very simple, this is an older electrical equivalent circuit. You can see they have used the European design of resistance, boxes. So in India we write the resistance as that, in Europe we do the box thing. The only other thing which is added here are these diodes. What do diodes do? They allow current to flow in one direction. They don't allow it to flow in another direction. This is a very simple model of human circulatory system. The human heart and human lung. And that might cause you some interest, right? So essentially what we are saying is that's our left ventricle, that's our right auricle, that's left atrium. And essentially we say current can flow in only one direction because as it is pumping, it's a capacitor, it's essentially giving energy to the system. The system then goes to the pulmonary loop where it gets filtered, and we have got RLC circuit equivalent there as well. And we also have the rest of the system. The blood also flows through rest of the system. So rather than monitoring each system as a different component, I have monitored the whole of the body as an RLC system. Now that's a very simple model. You can have more complex models just of part of this thing. And our biology colleagues also use it, because otherwise think of it this way. Heart is a very difficult organ to model. It's a very complex organ, right? But at a system level, how it works, we know. It's essentially transferring energy from one thing to these fluid. Fluid, we said a minute ago, we did this thing for fluids as well, right? Pressure is my voltage, flow rate is my current. So essentially my blood flow rate and the blood pressure becomes my voltage, blood flow rate becomes current. Now that's something which we can deal with. Okay? So of course there are people who have done more complex analysis. So this is from a Nature paper and only 2017, so not very old work, wherein they have looked at one side of the heart and blockages there and see if we can model that with an equivalent electrical circuit. If that doesn't convince you, let's take another example and then I will go back and force you to. So how do we walk? So people who design shoes or our locomotion system, we also work kind as an oscillator. The other day I showed you, what do? We do tuck, tuck. So our body is moving as a sinusoidal oscillator. So we could have done a more complex modeling as a van der Waals oscillator, or we could think, is that an RLC system as well? So a very simple system, if I'm looking at just one leg, would do something like this. Let's assume all of my body, rest of my body, this is a running, it's just a mass connected with a spring constant to this my mass which is moving here. And that is in touch with the ground. So ground becomes this, and I have got a spring constant and I have a damping, and this has got a mass which is moving, right? So I'm applying a force, that is applying a force on my legs. The force will only get these two. They will either be, it will either move or it will be stopped from moving. So I can model that system as this. And there are tons of paper on how to model the human body. And there are more complex models. So this is just a 2 mass model. There are 3 mass models. There are mass models wherein the upper body is considered a big mass, and inside the upper body we have a small mass. So it depends upon how many masses you want to divide, right? The hands could become a mass of their own. So essentially you can transform the human body is this lumped mass model. And once you have the lumped mass model, you can take it to a electrical engineering model. And then we know what we are talking about. Okay? So hopefully that's enough of a motivation to go back and do the exercise. I mean, we could have done the human heart model. It's not a very difficult model if you see the simple model which I have taken. All it has is a capacitance for each 4 corners of our heart and a diode to stop fluid from moving backwards. Right? You can see how heartless we are. You replace even the human heart with a capacitance. And the lungs, well, they have got some resistance to flow of blood because they are filtering. They still provide some energy there, and that's about it. And the rest of the system can be more. Remember, just now I modeled the whole body with one mass. So you can model the rest of the system. Now, all these inductors, what are they? What were inductors in our equation? They were the mass, right? So inductors replace the mass of the system. What were the resistors? They were the dampening system, right? And so every other fluid body part which is stopping liquid from flowing becomes the damper, and capacitance becomes the stiffness, right? Okay. Now, of course, you can say, but Professor, we do have these. The blood does not flow backwards, right? Arteries and veins, they have got similar design. We haven't modeled them yet. But if you're just looking at a top overview, how is my liquid flowing? If all I'm interested is how is my blood flowing in the system? I can use that very simple model to appreciate that. I can also go and just model one part with a bit more complex model. So here that's your supraortic vessels. This is your arteries. And again, I have modeled the arteries with a arteries stop. I mean, there is a natural resistance for blood to flow, and then there is a pressure energy being provided by the heart. So that could be our heart model. Okay? With that, I want you guys to translate this into an electrical circuit. So draw this on your notebooks, and then I will give you the equivalent table. You might have forgotten what becomes what, right? And then we will see an electrical circuit to that. Must confess, when I read these papers for the first time, like, seriously? That simple circuit, and they're publishing a paper out of it? Our professors used to give it to solve in undergraduate, these simple circuits. Similar thing you can do with textile. Textile moves in a certain fashion, so you can model each part as an RLC circuit, as a mass spring damper, and then once mass can become a RLC circuit. So my first order says 2 spring constants, 2 stiffnesses. So what will I get? 2 capacitances, 1 damper, 1 resistance, and 2 masses, 2 inductances. Oopsie daisy. So have you guys converted it? You have drawn the circuit with you, right? In case you have forgotten, that's the table. This Friday is a Valentine Day, right? So if you have a significant other, you can draw a circuit to him or her and give it. The relationship will not last after that. That will be the end of it. So when I was getting married, my mom asked me that bring something of gold to give to your wife. As you know, we don't get time to go to shopping. So just leaving my lab, it was late in the evening, and I realized, hold a second, all my chips have pure gold wires, right? The bond wires are pure gold. So I brought a chip. My medical wife still doesn't understand what it is. It's 24 karat gold, for 23 point something karat gold, right? And I know it's pure. I have purchased the gold bar. There was a friend of mine in Glasgow who has this research topic. He takes diamond transistors and then tries to put gold bars onto it to connect. And everyone else thinks, what a waste of resources. You're using diamond and gold to make circuit. But diamond is a very good material. It's very biocompatible. So if one can make circuits from diamond, it can go inside your body and stay. But still, we electrical engineers generally are funless people. Okay, so do I have the circuit? Can anyone raise their hand and say they have got the circuit? Come on, guys, I taught you for half an hour. You should understand this by now. Okay, I will give you the solution. This is what it kinda looks like. Okay? And if you forget everything else, that looks like a loop, so that becomes my thingy here, and the rest of it comes from there. Okay? When we do the tutorial session, we will do few other things, then I will come back and look at your work to see how you are translating it. Now, today we model the human heart using an RLC circuit, and we also said we can model walking. I want you guys to tell me an example what you think can be modeled using these. So you have seen enough things moving in the world. And we're not talking physical movement, liquid movement, water. We have seen all of this. So what else can you model using Sorry? Sorry?
Robot like.
Robot? Well, yeah, we could design robots as that thing. I was thinking something natural which exists by its own. And of course, we can model that as a RLC circuit as well. It's a constant motion, right? And we are giving energy to it. But this is an electrical system anyway. So you have seen things moving in the real world. Fishes swimming? Kangaroo jumping? Yeah, why not? That's similar to us running as well, right? You have seen nothing move in real life. If I were you, I will go trains move, planes move, I'll make all of them as an RLC circuit, right? When you go and see clothes, they're hanging on a rail. You just shake them, they start moving in a particular pattern. That's an RLC circuit for me. So, as far as I'm concerned, I can change entire world into an electrical circuit. It will be a very complex electrical circuit, but it will be there. Okay? Any questions in lumped mass modeling? No questions? So, in tomorrow we will go back to other type of sensory modalities, temperature, pH. And one of the reasons I went here was to tell the electrical or electronics engineers as to why we do all this thing and still doesn't look alien to us. Okay? Pure mechanical and mechanical sensors otherwise look very hard for us to design. But if you go in lumped mass modeling and the equivalent electrical circuit, we can still appreciate that. Good. Now, we have been doing a bit of camera design for last few days, and some of you have been having difficulty in understanding what these layers are, why we are doing it. Masters of VLSI would know these things, but let me grab some water. But some others did not know how a chip is fabricated. So I thought I will do the most boring lecture in electrical engineering ever. So anyone who is doing masters in VLSI or chip design people? There's no chip designer here. So all chip designers hate this lecture. I did as well. Because this is purely materials. This is how chips are made. This is one process after another process after another process. And generally this lecture is the best lecture to go to sleep. Okay, so this is why I'm doing it before lunch, not after lunch. But I'm doing this lecture not just to tell you how sensors are made, but also to introduce you two different aspects of it. One is, because we can make cheap sensors, and you have 3 or 4 mobile cameras on your phone. Right? Your phones also have a gyro, it has maybe even a temperature sensor, an infrared sensor. This room might have carbon dioxide sensor. And that was a problem we did. And it's a problem of our own making. So we can make large number of sensors who then produce a huge amount of data. So good old way of directly measuring temperature from one sample and saying, yep, it's 30 degrees Celsius, it's hot, is not true, because we have a large number of sensors in any system. So we will see what to do with data which is coming out of a large number of sensors in a production system, which is our system. Okay? So to do that, I will first introduce how chips are made, what sensors go into this, what data they are producing, how many of them are there, and then you will immediately see there is no way on earth we can process them by ourselves. We need some sort of machine learning there. So we'll do a very quick introduction to the kind of machine learning system we use. In the second half of the day, now remember, when I started talking about robot, I said we have got sensors, but we also have this thing. So we need to make that thing as well. The head, not the skin. Right? And head will be some form of a learning system. So in the second half of the day, those who already have done a course in artificial intelligence or machine learning, it will be a very basic course. We'll just see what is a perceptron, how it behaves. But we'll immediately see how do we make a perceptron. So most computer science people generally assume that hardware exists to run their deep learning algorithm. When the hardware doesn't exist, they just use a GPU cluster, a data center. There lies some problem. Do you know how much energy a data center consumes? So last Google's, Google's model, or so last natural language model paper which I read, the energy it consumed to train was more than the energy needed for a transatlantic flight. So you can fly 600 people from here to UK in less energy than it takes to train one neural network model. Now these days we are hearing a lot about artificial intelligence, deep learning and all that. If every problem is solved using deep learning, we do not have that much energy in the world in terms of power consumption. Right? And we will see why it is consuming that much power and what we can do to reduce it. Remember, our field, electronics engineering, we started as big computers. Remember in the good old days, history of computer you would have guys have learned, right? Computers used to be as big as the room or as big as an apartment. Actually, the first time one of the computers was powered on, it brought down the electricity of the whole city down. They were that big machines. So we went from that big machines and we kept on making them smaller and smaller to this. I mean, this has more computing power than early massive computing machines. Our computer science colleagues don't like this. So they are going backwards to big machines. Their machines are data centers, centralized machines somewhere else. And that for physical people like us is a problem. If we have a data center running for every institute, every city, it will require a huge amount of power. We can't provide that much energy. So we need to start thinking, if we go down the same route, we need to design our machine learning system in a slightly better fashion than ones we are designing right now. Because right now, the hardware which we are using, GPUs were not designed for running neural networks. They were designed for displaying high-speed graphics on computers. We are now stacking these GPUs to do these multiply and accumulate operations. So that will be our next border or next fence for electronics engineers to cross over, is to design new computing hardware, new chips which can do all of this neural network on a chip rather than a big cluster of systems. But before we do that, we need to see how we make our current chips and what the problems are there. Okay? Whenever you guys want to take a break, do let me know, because this is now my territory. I can keep on talking it for hours and hours. The paper to read is a paper by Rebecca Bush, one of my PhD students. What we're interested in is, I'll be telling the story from a slightly different angle. So we make chips. Not all the chips work. Right? Generally, we make chips in a wafer. So there will be a big round circular structure and we'll be making square chips there. Some of these will not work. Now, the other day we looked at manufacturing of chips as a costly business. We're looking at billion-dollar investment. If some of our chips don't work, that's a wastage. So ideally, we would like as many of our chips to work as possible. That unit is called yield. What percentage of my chips are functional? Okay. To understand how a chip is being made and how we can predict what percentage of my chips are going to work, we will take the simplest circuit possible. All of you know what an inverter is, right? There is an NMOS below, a PMOS on top, and if you give 1, it becomes 0. If you give 0, it becomes 1. A low voltage becomes high voltage. A high voltage becomes low voltage. So a very simple circuit like that. Now the reason why we can use it is most of chip design, except for analog people, is a combination of transistors in one form or the other. We looked at image sensor design, there was 3 transistors. Here we have one of each, NMOS and PMOS. If you can understand one of each, we can make any circuit possible. Now the physical layout I explained to you kind of looks like this. If I do a vertical cross section of a chip, if I cut the chip one way, what we will see, there will be a P substrate and then either a P well or straightforward N-type diffusion. And there we are forming an NMOS type transistor. We will have a small oxide followed by polysilicon, followed by metal, and then on the N well we will be making P-type structures. Remember that the other day somebody asked, why is the diffusion red? In this color, the diffusion has been selected as N, as green, and P-type diffusion as whatever color this is. I'm partly colorblind. I can only identify red and everything else is boring. Okay. Now, to the foundry people, and this is metal. The blue lines is the top, is a metal which is just connecting. So this metal is connecting from here to here. And you separate these with these dotted lines. These are just oxide. They are dielectrics which is separating this. Right? So this is what, when I ask my foundry to make an inverter, will make it. But we have done a very good thing in microelectronics world. We have separated manufacturing from design. So electronics engineers don't care about how it is made. Metallurgical engineers don't care about what they are making, as long as we give them a design. Okay? By now you would have learned that I abuse all other departments of engineering except mine. This is the training of our Warangal to me. We are best and full stop. Okay. So let's see, in order to make this, what do we need? So generally we start from the bottom. We start from the bottom and then we deposit things on top. So we need that P-type thing, between the P-type substrate. So we need a P-type substrate, and then from there we need to form these N-type diffusion or P plus type diffusion. Okay? So we need to do some form of diffusion or ion implantation. So we need to, so if I start with a silicon, in order to form N-type, I'll be adding some sort of phosphorus, and to form P-type, I'll be adding boron gas. Okay? We also need a dielectric to form the gate. So this is dielectric is the gate, and also need dielectric to separate between different materials. Now to some extent we generally use a silicon dioxide as dielectric. Silicon is already available, just oxidize it, it becomes a good dielectric. Not for the gate. For gate we used to use silicon dioxide earlier, now we are using high K dielectric. Okay. Now we call this material MOSFET, metal oxide semiconductor field effect transistors. We don't use metal. In the transistor, metal has not been used for a long period of time. We use polysilicon. The theory of it is based on the work function. We're not going into this, so take my word for it. We use metal to connect between different structures. So we need metal and we need polysilicon to do that. In metal, historically we used to use aluminum. That was cheap, easy to make. Nowadays we use copper. Copper also has got good conductivity. Right? In past it was difficult to make, now we know how to do etching of copper. We could have used silver and gold as well, but gold diffuses in silicon. So CMOS foundries don't want gold to come anywhere near them. But once a chip has been made, then we use gold to connect to it, because gold is a very good conductor. Right? And this is why I could never understand why people waste gold in this, you know. They carry the whole bank on themselves. So my apologies to all of you girls. Right? And people give gold gifts. I mean, if you go to a wedding, which I attended a few days ago, people are giving gold coins or gold bars. What's the use of that? That's just going to sit in a bank. Right? I could make much better use of that gold bar. I can have so many good connectors made in my chip. But no. Now, this is the side view. That's not what we design. As designer, we design the top view. Okay, we give the top view to the foundry. So top view of this will look something like this. Because we have no control on the side. Right? How much is going, that's defined by the foundry. How much dopants are going, how thick the layer is, that's not our control. We only determine how long and how wide our thing should be. So we basically tell to the foundry, okay, here, in this region, deposit diffusion. Here, this region deposit diffusion. This region deposit p-type diffusion. Deposit this as my gate. No. Okay. In this region, deposit p-type structure. In this region, deposit. So we basically tell to the foundry where to make what. Foundry doesn't care about whether it is connected properly or not. They will make it if you say make. I mean, by mistake, I could have just drawn a big metal wire here and shorted everything. Foundry will still make it. It happens to us quite frequently as students. Now, foundry, what the foundry does, there's a reason I have put them in different colors. Because remember, each one of them are being made in different height. So when I send them in different colors or in different layers, foundry divides these into individual masks. So they say, okay, that's where my N-well is going to be made. This is where my polysilicon is going to be made. This is where my diffusion is going to go. This is where my P diffusion is going to go. Finally, this is where my metal is going to go. And each one of these layers is made one at a time. Okay. Now, generally we use this term feature size to determine which technology we are using. So a 350 nanometer or 0.35 micron process is making the smallest structure of 350 nanometer. In past, it used to mean that's the smallest size of transistor, but you guys have seen it's no more the smallest size of the transistor. We also make these chips on a wafer, which is generally circular. For example, 300 millimeter wafer is now the standard. But if you take a 22 nanometer foundry in 300 millimeter, we are making 10 to the power 12 transistors. No chip needs that many transistors right now. So generally on one wafer, we make many sub-chips and then we cut them. Okay. Wafer thickness is fixed. It's not in our hand. So a 300 millimeter wafer would be roughly 775 micrometer thick. For those of you who can't appreciate these numbers, your hair is 100 micrometer thick. So take 7 of your hairs and that's roughly the thickness of my wafer. Okay. Transistor size as well, take the hair thickness and cut it in 1,000 times or 100,000 times and you will get a transistor. Good. So let's make this thing. So if this was not boring, wait for the metallurgical part to come now. So start with an substrate. Generally, the P-type substrate are already made for us. Should I take a break? Break lena? You continue karna? Break? Okay. Even they realize that subject is becoming boring. Let's take a break and we'll come back and we'll see the fabrication. Then we'll see where we need the sensors. Okay. Of what's happening, the next half will be more interesting. Okay. So we need to form a silicon dioxide first. First we cover the entire surface of the wafer with a dielectric material, because first it's an inverse process. Rather than making the thing first, we first protect the area where we don't want to make things. So to oxidize this, we'll either use oxygen or water. And generally hydrogen, water is quicker, easier, but then you have to remove hydrogen out of it. So that causes more problem. So once we have done the oxidation, then we need to identify the area where we are going to put things. So we do it by some sort of a lithography process. So first we deposit photoresist, a material all across the chip, which is a UV sensitive material. So if you shine UV light on it, it will melt. Okay. And generally you spin coat the wafer. You put a drop and then spin coat it and it spreads out, and then you have got wafer all around it. And you have different type of photoresist. Some are positive, some are negative, of less interest to us. Then what you do, now you knew this was the area my designer gave me to make the N well, right? The mask, the first mask is there. We shine UV light through it, okay? So all the photoresist below this, that softens up. Essentially, we cut a structure like this, okay? So once we have done this, now we need to remove the oxide below there, because we are going to form N well here, right? We are going to diffuse some material and there. And this is done through a process called etching. Now, etching is a harsh process. You pass hydrofluoric acid, and then that starts eating away the material. And then you have to be very careful. I mean, if you allow it for too long, it will start removing the silicon there as well. Now, this is a wet etching process. You also have a dry etching process. Okay. So once you have done that, you then use a piranha etch to remove the rest of photoresist which was left. Now, this silicon dioxide is going to protect the rest of it from being formed. Okay. And then we pass some dopant gas, arsenic or phosphorus, at generally high temperature, 800 to 1200 degrees Celsius. So that dopant enter the silicon substrate and it go from p-type to an N-well formation here. Okay. Now, this is the process which is a bit tricky, because based on the temperature, pressure of the gas, you could have lateral diffusion. Things could go this way, and you can see there's already some. And even though I have drawn it as a rectangle, it never forms a rectangle. It's always a structure like this. Okay. Now, controlling this is tricky, and this is where foundries have inherent recipe, what temperature, what pressure they are going to, and that control takes a long period of time. And once controlled, you don't change it, because you change, things could start behaving badly. Once you have done that, then you again apply hydrofluoric acid throughout the structure to remove the oxide. So remember it this way: oxide, oxidize your structure, put photoresist on it, put the lithography mask, remove the photoresist from where you are going to form structure, etch, remove the oxide where you are going to form the structure, remove the photoresist, form the structure, and then remove the oxide. This sequence happens with every layer which we are going to form. Till now, we have only formed N well. The same sequence repeats for every layer. Okay. Forming polysilicon, you form the gate first, and then you form the diffusion. I'm going a bit faster, so basically you're saying this is where you put diffusion, that's where N-type material will be formed, this is N-type, and then P-type material will be formed there. So it's pretty much similar process. Sorry, I should have told you what we are doing in N-type diffusion. So, you know what? So diffusion, the structure is called diffusion. Remember, in the layout also we called it diffusion. It's no more being used, diffusion, the process is no more being used to make these layers. We still call them diffusion for historic regions. The N plus is now being formed mostly by ion implantation in smaller geometry process. Okay. And the same process again. Repeat, repeat. Similar process, and now you dope with boron to make the p-type structure. We had made the n-type structure, now we make the p-type structure. And then you do deposit metal. Now, in modern processes, you have roughly 5 to 10 layers of metal on top of that. Okay. Generally, modern processes also have dual well. We only formed an N well. We would also have a P well in modern process, and the transistors will be placed. The N-type transistor will be placed in a P well, and P-type transistor will be placed in an N well. The other thing which I said we have changed, moved to copper. Now, I've gone a 5-minute quick summary of how to make a CMOS chip. There's a reason I went through this. Each wafer goes through several hundred different process steps before a chip is made. Think of it this way: we had 6 or 7 steps just to make N well. Right? If I have 12 metal layers, diffusion, oxide, I'm already in 12 plus 3, 15 into 6, 90 different steps. And I have taken a very simplistic approach of making this. Right? Each one of these steps can induce an error. What if my boron went too high? My doping concentration changed. My metal got deposited where it should not be, which has short circuited the circuit. Also have several parameters to control. Temperature being a very good parameter. If I'm sending a gas, it will be the gas flow. If I'm spinning it, it will be the actual speed of spinning. Now we generally monitor each one of these parameters. So we measure, so remember, sometimes we are heating the wafer to 800 degrees Celsius. Sometimes we are sending hydrofluoric acid, and there the time becomes a factor. How long am I putting this thing in hydrofluoric acid? So all of these we monitor very closely, and we have sensors to measure each one of these parameters. Okay? And after each step, we also measure things like how much things have been deposited. So we do layer measurements there. As you can very quickly see, I have 100 process steps. In each step, I have got about 50 different sensors. I have 5,000 different data sources, not data points, data sources. Right? Temperature sensor, pressure sensor, timing monitors, and so on and so forth. So, and now we are collecting a time series data of this. Right? Over a period of time, look, if we started hydrofluoric acid formation there, the temperature was, and temperature doesn't remain constant. In any place, none of these remain, they are fluctuating. Okay? Taking this whole data as a whole is virtually impossible to do any processing. Foundries do collect this data, but and we have this thing called fault detection and classification. I mean, there are some things which we know will go bad. If the moment we see the whole chip has been covered with metal, that's it, forget it, throw the wafer. Okay? The problem happens is, what if we go through the entire process, make the chip? We can't test every chip. Testing every chip will take a long period of time. Testing one chip takes a long period of time. Think of it this way. I have, let's take a very simple chip, okay? 10 binary inputs and 1 output. That's a very simple thing. How many possible combinations of inputs are there? If I have just 10 lines, each with 1 or 0. 2 power 10 input possible combinations. Testing for all 2 power n is going to take a lot of time, even if I have an automated tester. Modern chips will have something like 144 or 244 pins. So applying different input condition and checking the output for each one of them will consume a lot of time. Modern chips also have inbuilt self-testing facility, particularly digital ones. Analog ones are tricky to have best. The process is costly, and we would like the yield to be as high as possible. More importantly, it would be good if we can tell how many of my chips are going to work from this data which we have collected. Now, one can imagine if my production data changes, my output system will also change. Temperature change slightly, the dopant concentration will have been slightly different, the device performance will be slightly different. The other thing I keep on talking from last 2 days are no two transistors are exactly the same. So even transistor made on the same wafer, one side would have got more boron doping, the other side would have got slightly less boron doping. That will change the transistor. And then from one day I have made something, the second day I make something, there will be slightly more changes in the system. So we live within a certain tolerance of change. Right? If it changed by X%, I wanted to sell a chip at 2.2 gigahertz, rather than 2.2, it's 2.21, I will live with that. If the performance is 1.7, I can't sell it as 2.2. I might sell it as a 1.7 gigahertz chip. But if it's 0.5 gigahertz, forget it, I have to throw the chip away. right? So it will be good if we can predict the yield, if we can tell without testing how many of my chips are going to work. Now it so happens, secret, no foundry ever tells the number. Entire foundry business is a closely guarded secret. Know the steps. I told you steps. We teach the steps. But what's the exact temperature? What's the exact pressure? How long it is done? It's a very closely guarded secret. Even the ones which I know of my fab, I will not tell anyone else. Because it has taken a long period. That is our intellectual property. All chips are now being made by the same sequence. The devices are same. The material is the same. It's just the mix of process steps which is slightly different for each one of them. Okay, some of them have patents on high K dielectrics, only they can make few nanometer chips. The devices to make photolithographic kit are export controlled, so only few countries can make them. So I can understand, but otherwise the sequence of steps are fairly well known. Okay, so which also means, so our task, we're working with a German foundry, was can we predict the yield based on the process parameters which we have collected. So we have a huge amount of data which we have collected. In past, we have also measured the yield, how many of the chips were within average performance parameter. So rather than this ability to measure, can I tell beforehand that if you go down this route, the chip will work or chip will not work? Can I predict the yield? The other issue is there are two things which are issue here. One is knowing exactly what percentage of my chips are working. 95% of the chips on this wafer will work. Or I put a threshold. If I'm making less than 90, that wafer is not worth selling in the market. Because even after the wafer has been cut, I need to dice, cut my chips, package my chips, and then test it. So it's going to cost me more. So if I can just say, you know what, this is below my threshold, don't test it, even that would be okay. So I have two problems now. And for computer science, these two problems become the classification problem, good versus bad, or telling exactly what's the amount, how many of my chips are going to work. So the good versus bad problem is slightly easier. The regression problem, telling exact value, as you can see, would be slightly harder. It becomes even harder because no foundry makes their data public. It's not that you can, it's not like computer science image databases which you have, wherein most of you will, a number of you will do your project, run a new neural network algorithm and look, I can identify human beings in the picture. This data is not public. The only way you get is if you're working with a foundry, people like us who had access to some of this data. The classification problem has been studied by a lot of people in past. The regression problem has not been studied. So I'm going to give you an example of a problem set which we studied as to how it worked. Okay? So now I'm slowly moving you towards the brain part of the robot. Now before that we do just a quick summary of the kind of algorithms which are there. So have you guys done data structures in your bachelor's? Right? So you have learned about trees, decision trees. Smile on some of your faces says yes, we remember hearing that word. So we would be using a very simple structure called random forest, which is essentially a combination of very small classification trees. So you make large number of classification trees. Each tree tries to classify the data. And in the end, you do a polling. If majority of my tree says the data is good, you say the data is good. So rather than making one large structure, you make several small decision constructs. It's like asking all of you guys, is my lecture boring? If majority of you say it's boring, then it is boring, right? So that's what we are doing. We are not having one expert classifier, we are having multiple small expert classifiers. Okay. I will not dealt you with how random forest is made. It is on the lecture slides online, and you can have a look at this. There are other algorithms like k nearest neighbors as well, which basically try to look at how many people are close to me. If I think this is good, how many of them are in this basket and how many of them are in the other basket? You just try to find in a space how many of them are nearer by. Anyway, I will jump into the data to show you how complex this can be. So we looked at 35,336 wafers which were made over a period of 6 months, okay, in a 350 nanometer auto foundry. So the chips were made for automotive production. Now, automotive chips are always made 1 or 2 generations behind the commercial chips, or many generations behind the commercial chips. You know why? So all moving things like aeroplanes or cars, we don't use the most modern chips, generally speaking. The ones which are used in consumer electronics. Could you think of a reason why? There are few problems in modern chips. They have not been tested for long enough. You buy a mobile phone for 3 years. You don't buy a car for 3 years. Right? You don't buy an aeroplane for 3 years. If your mobile phone hangs, it hangs. You don't want your aeroplane to hang mid-air. Right? So you don't have the luxury of errors introducing the Simpson. The other thing is this, a number of our chips, an automotive and this face very high temperature. And think of the sensor which is sitting next to the engine looking at the oil level. Temperature could easily go 300 or 500 degrees Celsius. That's not the same temperature which your chips go. Okay? Unless by mistake you end up cooking your chips or putting your trousers, your mobile phone in trouser and putting in the washing machine. Okay. Good. Now, at this point you might say, okay, 35,000 wafer, each wafer having loads of data samples. Now this is where the real data becomes problem. Not all the time data is present. Some of the sensors could have become switched off at that time, or they were giving erroneous data. When you have large number of sensors, you can't expect all of them to be giving true data at the same time. Okay? So there were data missing as well. And this happens because a number of other factors. Okay? And not every machine gives the same sensor data. So if I have, say, an etching machine, I thought it had 5 sensors. In one run, I got the data from all the 5 sensors. Another run, I only got 3 sensors which produced my output. Okay? So a vital step in almost all of these steps is to pre-clean the data. Now, I have got a huge amount of data here. Let's have a look how much data I have. Oh, I haven't given the data number here. Okay, will come the data number anywhere soon. So we could not deal with these large number of sensors. We had roughly 650 different parametric steps, and we wanted to come up with one output here. 650 input measurements, one output, good or bad. That's it. That was too large a space to train a small neural network. If you're running a neural network on a GPU cluster, then that's perfectly fine. So we tried some data processing, and we looked at a wrapper feature selection method to extract what are the prominent parameters, which parameters cause the most change in the output. And we reduced it to about 323 parameters. Okay. Even that was heavy. We then started doing principal component analysis or Boruta analysis, which again we looked at which of these input. Now we are looking as parameters. We don't care whether they're temperature data or pressure data. They are numbers. So from one of these numbers, I'm trying to get an output. One output will be good or bad. Another is yield. Is it 90% correct, 80% correct, 70% correct? So I looked at this comparison matrix, and Rebecca found that a large number of these sensory data, or a good number, were actually not causing much change to the output. By their internal actions, yes, but individually they are not causing much change to the output. There were some which were doing big change, the green ones, and there were some which were in between. So we took this data and we iteratively kept on checking. So what if I remove this data point? Does it look still valid? If I remove the other one, does it look still valid? If it doesn't, then I put it back. So we ended up with about 190 odd data samples. Okay. Now, each one of these, so remember a chip is going through multiple processes. In each process I have 320 data samples, which I have reduced to 190 data samples. Now, the sooner I can tell that my wafer is going to go bad, the more money my foundry will save. It will stop the rest of the processes. Okay? So if I can just tell after the first process, hey, this sample is not good, and there's no direct relationship. It cannot say that one temperature caused the wafer to fail. It could have been a sequence of events which would have led the wafer to fail. Okay? So this is the kind of our result after training this neural network, training this random forest system. Now, the dots are, so on y-axis I have the obtained yield which I have obtained. On the x-axis I have predicted yields. Ideally speaking, it should have been a straight line, because some of these chips were measured. Of course, we're not going to get straight lines. What you can see for things which are good, high yield, I've got a very good prediction. These are going to be high yield. For the ones which are bad, I cannot find. I mean, ideally this point should have been here. So the predicted yield was, say, 85%, and I was getting 81% kind of thing. But what I'm okay in predicting is this is going to be a bad wafer. I cannot tell that 60% of the chips will work, but if my cutoff threshold is 80%, anything below 80% is bad, I'm okay in telling good versus bad wafer. This is after one process step, right? We were looking at a system with 4 processes, one after. So even after one process step, I can say I can identify 99.37% of the good wafers and 97.98% of the bad wafers. These numbers look good, they are not good. So if my 2% of my bad wafers, remember I had 65,000 wafers, right? In 65, each wafer would have got roughly 1,000 chips. So 65,000 into 1,000 chips. Okay, I did wrong prediction on 2% of these. So 2% of 65,000 will be roughly 1,200-ish. 1,200 into 1,000. I'm sending 1.2 million bad chips in the market. Okay. So despite the fact from a computer science prediction point of view we are very good, you can pat on the tab. You look at the actual number, things are still problematic. When you look at all process steps, we of course significantly improve. Now we can predict 99.38% of good chips. So we only miss about 0.6% of the wafers. So few wafers we missed, and 98.78% of the bad ones. So we are doing much better approximation when it comes to that. Of course, one question which we were asked is, can you do the inverse? Can you now tell me which process step to improve to get a good yield? Or I'm going down the bad design, can I change something later on to improve the process to become good yield? We tried that and miserably failed. What we could say was that if something has gone down this route, whatever you do, it will not improve. But we cannot predict the exact amount of yield till now. There's a work in progress. This is not the final work, but the inverse solution we have not been able to answer till now. So given a set of sequences, I can tell whether it's going to be good or bad. But then to say which one or which few of the parameters to change to get a better yield is still a very difficult question. And you can imagine, I started with something like 600 different parameters. I've got one output. From one output going back to say one of these 650 or 5 of these 650 is challenging. Okay. Now, I went through a very quick summary of how to make chips and how we did one work on predicting the yield. That looks good, but it still required a good amount of computation power. It runs overnight. I cannot tell live as my data is coming that, hey guys, stop. And that's the problem. A large number of artificial intelligence algorithms cannot work live. So I went quickly here, and then I will also go, if I can. So now comes the second part of it. So that was running on a computer, on a GPU cluster. How do we actually make these things? Do you want me to stop, sir?
Yeah, actually, I want in the afternoon also we have to be still only.
Okay.
Afternoon this lab is busy with some.
Okay. Well, go through.
That's why we maybe just tell that a release file or something, if it is available freely, they can download.
Now we can run theory, sir. That's not a problem.
Yes,
We'll do tutorials. Problems. Okay.
and otherwise, free software if it is available. We can
Now, if you want a book on how to understand neural networks, there's absolutely no shortage of books. There are many thick books in the market. Many of them talk the mathematical basis of neural networks, and you can delve yourself into it. Remember, a number of these books were written for computer scientists and for mathematicians. We don't like that many algorithm code or these things. There were some which I really liked. This is Simon Haykin's, which cover a good details. And then there is neural network design. This is a free book which is available by Haga and so. And I really like this interaction because it goes fairly basic works. There are some others which I have found to be comparatively easier to follow for my students, and I would recommend the same to you guys. I'll just jump into this. I've already covered this. Okay. Now, what our nervous system or any brain would do, it will take a stimulus. The stimulus will be translated into an electrical signal, and it will go to a neural network which will do something with it. Okay? The thing which does something with it is this. We don't know how it works. Okay? Let's be very clear. We know which part of the brain does what. For example, our visual cortex is here, our auditory cortex is. So we have labeled various parts of the brain as Brodmann areas, but we don't know how they actually work. What we do know is it has many of these inside it, the neurons, which have got kind of a structure like this. It has got a central body, a long tail, and then few other connections. So they talk to one another. What we also know is we have a large number of these, got roughly 10 to the power 11 neurons, right? And they're densely connected. Each neuron is generally connected to 1,000 or 10,000 other neurons. They talk densely with one another. But the other problem which we know is that they are very slow. The speed is roughly of the order of a millisecond. Okay? How fast are our logic gates? We've got few gigahertz clock speed, right? And we are saturated actually. We have stopped ourselves at 3 gigahertz. We could easily make a 10 gigahertz clock speed per. We just don't know what to do with it. The question then comes is, how does a machine which is working in millisecond does all this computation? Whereas we working at gigahertz are still finding it difficult to do. I mean, you guys can hear my talk and ignore half of what I'm talking. You are doing that. You have to do that, or else you cannot store all that information. Right? You are seeing to my scene and you are ignoring half of what you are seeing. And your brain is immediately thinking, nah, 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 nah. A poor computer has to record all of this, compress all of this, and then extract information out of this. So we compensate for our slow speed by massive parallelness. It's way more parallel than our common gates are. Our fan out is of the order of 3, 4, 10. Right? Here, each gate is connected to a large number of these. We also have a 100-step rule in neurons. Computation does not take more than 100 steps in our brain. This is primarily due to power requirement, power and time. If we can't decide within 100 steps, then we are in trouble. Many of our algorithms take much more than 100 steps to do that, any operation. Okay? The other thing which we don't know how it works is, remember I told you neuron is connected to many other neurons. The amount of information they share is actually very, very low, at maximum few bits. So when you are seeing a picture, it would have been taken by roughly 100 million odd pixels. It goes to 11,000 cortical neurons going to the brain, where these neurons extract few bits here and there, and they're trying to make a picture. So we don't know how that works. How do these gates, only sending few bits of information with one another, are able to do this complex operation? The other thing is, the brain is very plastic. It's not a hardwired computational machine. We are born with some hardwired structure. Rest of it will learn with time. Right? Our eyes, I mean, when we are born, we can only see till about one hand distance. We start seeing with due course of time, we recognize features. We're not born with language and other features, okay? So that's how our brain does. Let's see what is a neural network. So by now you guys should know what a neural network is. I'm sure you have heard enough of this word in your undergraduate, postgraduate. What is a neural network? Every system has input and outputs. So how is a neural network different from a normal system like op-amp? Now you can have a neural network with one layer. Multiple hidden layers will be a deep learning system. If we have one or more inner layer, that's a deep learning system. Okay? The definition, if you take Alexander and Morton's 1990 definition, would be something like this. It's a massively parallel distributed processor which has a natural propensity for storing. It can store information. Okay? It stores experimental knowledge. It kind of resembles brain that it acquires knowledge through some learning process. We did not say it learns the same way the brain does. Okay? It's similar, it has got a learning process to learn. And then the storage is through the intersynaptic weights. The weights are between two different individual neurons here. That's where the storage is. That's the only similarity between our neural network. Well, you can try to, but most neural network and human brain have that common feature. They learn somehow, and whatever they have learned, they stored in memory between two individual blocks. Now, we need to start to make a network, we need to start with a neuron. Okay? And this, many of you might have already seen. A typical perceptron or a neuron looks like this. It takes n number of inputs, multiplies these inputs with weights, which are my stored memory elements, adds up all those weights, and then there's an activation function which judges, are these some function more than a threshold, less than a threshold, or they are in particular, there will be a function which will give kind of an output, which will be a compressed output. Okay? And based on whether my output does what I want or not, if it already does, I don't do anything. If it doesn't do, if there's an error, I then go back and update my weights. The theory is if I do it a large number of times with known data, I will learn how my input data is related to my output desire. The activation functions could be, you could have just a step activation function. If the sum data is below a certain threshold, my output is 0. If it is below, my output is 1. Or you could have a tan H or a sigmoid kind of function. Have you seen a function like this in electrical circuitry before? This or that? Sorry? Okay, is there an electrical circuitry which can give me this response function? Remember, all of this I'm training on how to make these. We are hardware people. Actually, an inverter kind of have an output like this. Yes, to 0 it makes 1, 1 it makes 0, but it doesn't do a sharp change. There's always a smooth change. Right? A differential amplifier current has got a response function like that. Okay. Top of that, we will have a simple feed forward network where data just moves in forward direction. And if you place a hidden layer which neither sees data from input nor sees data from output, you have got kind of a deep learning system. In modern days, of course, we have large number of these hidden layers and we have got some form of optimization to do this. And we kind of have a two-way flow in these layers. The function flows in forward direction, the error propagates in backward direction, and you propagate the error and try to do this. So how many of you already know the operation of perceptron? Do I need to teach how it works, or you're happy how it is trained so that I can jump into making these? The head shaking, translate this in English language. You know it, you don't know it. You don't know it. Fine, that's perfectly fine not to know. Right? As I said, if needed be, I will go very fundamental and then we'll go proceed. Okay, then let's try to make a perceptron in next 15 minutes. That's what my own teacher has asked me to stop. Let's see how far we can go. So let's take a very simple system. I'm taking the simple system from the book which I mentioned earlier. I want to make a single learning system which classifies between two inputs. So all I want to do that, I've got a assembly line production system where fruits are coming in, okay? And I want a neural network. I've got tons of sensors which measure various properties of these fruit, and I want a neural network to identify whether my fruit is an apple or a banana. Now, as a human observer, we know immediately if it's an apple or banana. But remember, what's the IQ of computer? 0. It has no inherent knowledge unless you teach it. So that's all I want to do. I want to sort this thing into banana box and apple box so that I can put all the bananas on one side, all the apples on one side. A very simple problem. Okay. Now let's think. We have got 3 sensors which we have placed because we did not know what we are measuring, right? Priori, the system has no idea about its input. So let's give 3 types of sensors we have. One which looks at the shape, one which looks at the texture, and one which looks at the weight. Okay? And all it says, if the shape is round, I will give an output of 1. If the shape is elliptical, I will give an output of -1. If texture is smooth, output of 1, rough, output of -1. Let's take weight of 1 kilo. Weight more than 1 kilo, output of 1, less than 1 kilo, output of -1. At this point, your brain will immediately say, hey, that weight sensor is not needed. There's not going to be a banana more than 1 kilo or an apple more than 1 kilo, but I did not know that. As a neural network, I have no idea about that. I need to teach myself that. Similarly, if you would say immediately, the only sensor needed is a shape sensor. Unless you get a round banana. Do we get a round banana? Or an elliptical apple? Slim chances. Okay? So, in ideal world, my banana, the sensor output will be -1 for shape, it's elliptical, 1 for texture, it's smooth, and -1 for weight. And my apple will just have 1 for shape, 1 for texture, and -1 for weight. Okay? So that's my input criteria. I need a neural network to identify based on these two. And remember what we did, our neural networks are generally things like these. They take all these input matrix, whatever my sensor have measured, multiply it with weight. So whatever weights are saying, how important is this sensor data for my classification? Now you would immediately say the only data which is important is shape. Everything else is less important. But I don't know that right now. I need to learn that these two are not important, this is important. Right? And this I can learn by giving something. Okay, give me some apple, let me see if I can predict it as an apple. If I don't predict it as apple, then let me go and change my idea of how the world is. Okay? So essentially we are doing this. We have these measurement vectors, we multiply them with the weights of each one of them, and we add an offset. Why we add an offset, we will see in a short while. Okay? So let's take an example. So if that was my weight, my ideal weight vector is this. Okay? So -1 times -1 is 1. These two will become 0. If my output is 1, it's a banana. -1 times 1 is -1. If my output is -1, it's an apple. So that should be the ideal weight vector which I need to learn. That's what I need to store. Only consider this, don't consider these two. When I initialize the system, I don't know about it. So I need to learn that. Okay? So you can do apple and banana test like the way I did just now. Okay. If you give it an orange, that system will not work, right? Will it work with an orange? Because maybe your texture will become rough here. Now let's go through the theory of learning the weights. Now of course the theory is a bit more convoluted, but I will do we are doing a very simple example. So our neural network has got only one perceptron. Okay, we are training it with a single perceptron system to identify between these two. So we are doing something called supervised learning, wherein we are telling to the neural network, this is the right reply. Okay? For this input, this is the reply I expect. We are doing it for some set of data. Okay? And we are also doing something, there is something called reinforced learning, wherein we don't give examples, but the network grades itself, how good I was, how bad I was. Okay? And then there's also something called unsupervised learning, where we are not doing, we are just classifying. I have got a set of input, can I divide it into two groups? Okay? Telugu speakers versus non-Telugu speakers. Okay, that kind of thing. So let's start with, so I'll first teach you the theory of how learning happens, and my eye is on the watch to see if I can go quick and finish it in 15 minutes. Should I finish it in 15 minutes, or you want to have a slow process and we also learn it properly? I can finish the whole thing in 15 minutes, that's not a problem. Slow process. Which means you'll have to hear me for the whole second half as well. You're happy to hear me? Okay, somebody's happy. So the way it happens is, let's take the example of a 2-input perceptron. Okay? So for each set of input, I will have these. What is my measured vector and what is my desired output? What's my measured vector? What's my desired output? Measured vector, desired output. Okay. Was there a bell ringing somewhere? So you start with random initial weights, because we don't know what the weights are. Which sector is important, I don't know. You start with random initial weights, and then you start with the first input. Our first input here is 1, 2, expected output of 1. My random initial weight is 1 and 0. Okay? So I multiply these two together. So 1 times 1 is That's my 1 times 1 would be 1, plus 2 times 0.8 is minus 1.6. The sum together becomes 0.6. And the kind of activation function I'm using is a hard limit activation function. Anything below 0 is 0, anything above 0 is 1. So my output now becomes 0. My desired output was 1. So my network is wrong. Okay. What's my error? Error is 1. Okay. So now I need to go back and change my weights. I've done a wrong prediction. Now there are many ways you can go back and change your weights, and all these help on how quickly the neural network gets to the most optimum weight. Here we will take a much simpler approach, which is if my error is 1, my error is 1 here, right? I just add whatever was my input vector. Okay? All I do is I take the weights and add my input vector to it. Because if my error is high, its chances are high that there's some important feature which I am missing. So I started with 1, 0. I just add these weights to it. As simple as that. I get a new weight here. I don't know whether this is right or wrong. So what I do next, now let's pass the second set of data to it and see whether after adding these weights have I got my true weights or not. So once again I have got minus 1. Now these are my new weights, 2, 0. So multiply 2 with minus 1, 1.2 with 2. I get an output of 0.4. Hard limiting function gives me an output of 1. Still wrong. Okay. So initially, what's my error now? 0 minus 1. My error is minus 1. So what I could say is this is causing an error in the other direction. These inputs. So rather than adding, this time I subtract it. So I subtract the weight and I get whatever is the old weight, I subtract my input vector from that. So if it's both pushing the error in that direction, I add it, error in this direction, I subtract it. I'm doing a very simple operation here. Okay. So I get new sets of weights, 3 and 0.8. Let's try it with the third set of data. And once again, things to weight. If not, if my desired output is less than my actual output, subtract the weights. Otherwise, add the weights. Alternatively, if I do it in a more mathematical fashion, all I'm saying my new weight is my old weight plus error times my input. Okay? And same thing I'm doing for my bias as well. Now, bias is nothing but an input signal where the signal is always 1. Okay? So that's the mathematics behind it. Let's try to see whether it works for my apple banana problem. Oh, I am going to finish it in 15 minutes. Is it clear till now? Speed is okay? Okay. So once again, I have 3 sensors now. Let's see if this thing works. I mean, previously we just trained it, right? Let's try to train it. So why don't I start with a random initial weight again? And this is what you guys can practice on your own. You can give any random initial weight and see if the thing works. So we have started with 0.5 minus 1, 0.5. It's no way related to my desired weight. My desired weight was minus 1, 0, 0. Just far enough away from that. Okay? So and I started with initial B of 0.5 as well. So that's my input data set, minus 1, 1. Set of 1. I apply this thing again here. So minus 5 into minus 1 is, sorry, 0.5 into minus 1 is minus 0.5. minus 1 into 1 is minus 1, 0.5 into is this. I get a result of 0.5, I get an output of 0. I should have desired an output of 1. I am erroneous. When I have got a desired of 1, what I do? I just add the data there. Okay? I get new sets of weights. I do the same thing with the second set of data, and this time my output is 1, but I should have got a response of 0. My error is minus 1. I train it again. I reduce this number back to it. I'm aware I'm going a bit faster here, but I'm doing the same operation now. So once I have got, after 2 iterations, I have got a new sets of weights here, which is minus 1.5, minus 1, 0, minus 0.5. Now one thing you would have seen, only in 2 iterations, I went from, my initial weight was 0.5. I need this number to be minus 1. I went from minus 0.5 plus 0.5 to minus 0.5 to minus 1.5, very close to my desired thing. I know these two have not become 0, but we also know they are kind of immaterial. This alone is almost equivalent to sum of these two. Right? So I have come very close to my desired iteration in just 2 sets of iteration. And you can do that with a check. So I now check it for, say, one of the other features, the banana feature, minus 1, 1, and hey, that gives me 1. So in 2 training epochs, I train my single neuron to identify between apple and banana. Still takes longer than the time it takes to train my 3-year-old daughter. Apple, banana, and she will be doing apple to everything after that. Everything is an apple. And the same thing works for banana as well. So I give 1, 1, minus 1. Same vector, minus 1 in 0.5 into 1 is minus 1.5. This becomes 1, so cuts out, that becomes a hard limit of minus 1.5. I will get a result of 0. I finished a 2-hour lecture in 15 minutes. That should be good to me. Now, despite the simplicity of this training, I have taught a very simple training system, right? I'm just adding and subtracting. It will always converge to the actual weight if the weights exist. And there lies the beauty of this thing. Okay? A neural network is, of course, more than a single neuron. It's a network of such neurons. Now, hopefully by now you know how the basic building blocks works. Okay? In the second half, we will do more on how to make these physically. Okay? Unfortunately, we don't have the Cadence lab today, or else we would have made this network in Cadence. That's not very difficult to make. Okay? We ended up with 3 weights and 3 input vector. That's it. Okay? But we'll still see how we can make it. There are few things which are needed here. We need a multiplier. Do you guys know how to make multipliers? Electronics people, some of them should know. How do you make multiplier? There's head going up and down. So next question is, tell me the answer. How do you make multipliers? So what are the operations I'm doing here? I'm essentially multiplying 2 numbers, adding the 2 numbers, and then defining 0 or 1. That's all I'm doing. This is what we will try to do. We'll try to find the simplest way to multiply 2 numbers, add the 2 numbers, and then hope for the best. Okay? We're not going to be able to make a whole big neural network on a chip in 2 weeks workshop, but hopefully we can make a single neuron. Okay? We stop for now. Good, okay?
Hello, hello. Okay.
network is nothing but a repeated combination of same building blocks. Okay, so same perceptron repeats. How it trains, how it grows, that's least of our concern. Of course, it's of our concern as well, but because that consumes space, area, and all those things. But we will now see how we can make this, or how at least we can try to make it. Okay. We'll see many different approaches. So this is what we need to make. Okay. So what are the things it does? You have a stick? Where does the stick go? Or a projector? Yes, thank you. So what we have here is n number of inputs. In the morning when we designed our perceptron, we just had 2 inputs. Right? Now we have n inputs which are being multiplied to n weights. Okay. And then they are being added. So we have multiplication here, we have summation here, and then we have an activation function. These are the few things which we need to build. There are many ways to do this. You can have a purely digital neuron, in the sense that you could code it in Verilog, VHDL, try to compile it on an FPGA, and so on and so forth. The question then comes, where do we store the weights? Now you see, the highest amount of energy consumption in an AI system is not in multiplication, not in addition, but in memory fetch. Wherever you are storing the weights, the time it takes to go there, take the memory and come it back. Now the reason why it is that, traditionally computers were designed to be, just give me a second. So you might have seen a block diagram picture, something like this, in your first year computer science lectures or electronics lecture, what we call as the block diagram of a computer. So that was one of the earlier machines, the Harvard architecture, which tries to have the memory in 2 parts. There's a data memory and there's an instruction memory. Now whenever you are doing a digital operation, you're doing something on some data. That something is your instruction. Previously the instruction memory and data memory was kept separate. But the architecture which became very popular is the Princeton architecture, or the von Neumann architecture, which tries to have a common memory for both, or has a common memory for both data and instruction. Now, and then you have data moving from input to output. Now what has happened over the period of time, processors have kept on becoming faster and faster. We had the Moore law. Memory is also kind of becoming faster and faster. Not at the same pace, but it is becoming faster. But the thing which is not growing at the same pace is the connection between these two. The interconnect speeds have not grown too much. So we now have what we have been having this for about 2 decades now, what we call as processor memory bottleneck. So processor is fast, memory is fast, the interconnect is not very fast. Now this is another figure which I often talk about. So because of these microelectronics, I said in the morning, we went from machines which are this big to machines which are tiny. Our machines do not learn. Our hardware is not meant for learning. The traditional hardware is meant for running a program. You write a program, it runs the program. Now this is a slightly older result. This was, I think, almost a few years now when Google Brain project came up. And the idea was to identify cats in YouTube videos. To do that, the system took 16,000 processors and used 100 kilowatt of power. My daughter can identify cats in YouTube videos on a piece of bread. Not just one YouTube video, she can show videos after that and she will identify cats. Right? To some extent, it is because of the way we are writing code. So we hardware people have provided processor at a very low price. Earlier, the processor and memory was costly. We had big machines. So our software colleagues were nice in writing software. Now we have provided for cheap. They are being a bit liberal. So this is the performance memory gap which we see in processor and memory. If you look at the scale of improvement, these are not on any particular scale, but if we start with 1 in 1980, whatever was processor and memory at 1980, by how it has improved over the years, we have got a significant improvement by the time we reached even the last decade. Memory has also grown. You can see we have gone from 4 MB to 256 MB to 2 GB and so on and so forth. Now we are having multi-GB memories. But the gap in the performance has kept on increasing. Okay. One of the reasons for this gap in the performance, the devices themselves are performing slower. And second is we need to have data moving from CPU to memory and back. And for these we have buses which are off-chip systems. And buses are slow. To find solution to this, we started having cache memory. On the processor we started putting memory and tried different levels. There's level 1 cache, level 2 cache and so on and so forth. Now that system worked pretty fine, except when we are looking at a neural network, for every operation which we are doing, I need a memory fetch. I need to bring what was my weight. So think of it this way. I have a 1000 layer deep network. Each layer has, say, 100 neurons, each neuron with 10 inputs. A very simple configuration. So already for overall number of weights is 1000, which is 10 to the power 3 into 10 to the power 200 into 10. So we're looking at 1 million memory fetch just for one instruction. Okay. That causes problems. One could ask, why don't we build the memories then and there itself? Why don't we make a memory at the site? Now historically, the way we have designed memory is the same way we have designed cameras. We have designed memory as an array. We designed one memory element and we designed an array of this. So next part of this might be a bit simple for advanced students, but I was told that they are earlier students, so I should go a bit more simpler today. Let's see how do we make adders and multipliers. So we need to add and multiply, right? So how do we make adders in digital logic? You two should know this, right? So if I add two numbers, if I just do a half adder, so 1 and 1 added will give me 1, 0, 0, 0 will give me 0. The sum becomes an exclusive OR. A full adder is these two numbers plus the carry from the previous stage. Okay. So it's an exclusive OR. The carry is a majority gate. It selects either AB or BC or CA. Okay. So we can implement this in this circuit. I mean, that's a simple implementation. I've done the XOR gate as simple as one can, and we can do the C out there as well. This is multiplying 2 bits. 2 bits with so this is adding 2 bits with a carry. Can somebody count the number of transistors we have? And make a note of it. So if we have that many counters for addition and just addition of 2 bits, we would generally have 8-bit data. How many bits are your machines? 64-bit machine, just to make our life very easy, right? So let's assume all of our weights are also 64-bit and all of our input is 64-bit. So how many transistors will I need to make the adder? Let's keep track of this number. So I would really want you guys to count the number of transistors. Don't worry about whether they're NMOS or PMOS. Let's count the number of transistors. And please make a note of it. This number is going to exponentially rise if you're just right. So my majority gate needs 10 transistors, right? And XOR 16, is it? So I need 26 transistors just to make 1-bit adder. My end customer wants 64-bit precision. So 64 into 26 is what I need just for addition at one terminal. So at here. Okay. Now of course you could say, why don't we use the same adder for all of them? Of course we could have the same adder, multiply and do it in sequence. That will just make the system a bit slow, but for the argument, let's just go that we are making neural network as it is. Okay. So 64 into 26, we are looking at something like 900. 1664. Oh yes. So I have spent 1500 transistors in making one adder. And we decided to make a network which is 1000 layer deep, 100 layer on each node and 10 input, which is a small network, right? So we had 1 million neurons in our network, right? So we have 1 million adder needed. So 1500, let's take, I know 1600, but let's take a ballpark, easy to, so 1600 times million, right? We're already at 1.6 billion transistors. Doable? We are putting 100 billion transistors on a chip. Right? So it's not impossible. I can do that. But I have only done addition till now. I have not done multiplication. My apologies, I was wrong. We don't need the addition at each stage. So my brain is dead. As you can see, second half of the day the brain stops working. That's the adder. That's the multiplier. Right? So we're designing the adder till now. So I don't need an adder for each stage. I only need adder per number of, but I still need 1600 times, I said 100,000 layers, so 10 to the power 3 to 6. So 1 million adders I will still need. Okay. So that was the easy bit. Subtraction, how do we do subtraction? No, complement. No. We do 2's complement, not the 1's complement. By itself is 1's complement, right? What's 2's complement, second year students? Sorry? So invert everything, add 1. Okay, good. And I'm sure you can prove that 2's complement is actually subtraction. Okay. What's 10's complement in decimal number system? So if you're subtracting 3, you can think of it as, how is another way to subtract 3 from a number? So 5 minus 3, if I don't have a subtractor, how will I add it? I will add 7 to it and remove the 1. 5 plus 7 is 12, right? And if you remove the 1, I get 2. So 5 minus 3 is 2. So this rule of 2's complement works in every base system. In base 10 system, we have the 10's complement. Okay? Good. Now can somebody tell me how do you make multipliers in digital logic? Sorry? shift and add, because that's what the next slide says. And that's what we learned in our high school, right? The way to shift and add is da-da, 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 and then add them up. Which means I now need to compute all these partial products, each number multiplied by each number, store it somewhere, and even just I'm doing a 4-bit adder, I need 4 shift registers to store these individual numbers and then add them. Actually, each shift register now becomes an 8-bit shift register. Okay? So essentially my operation becomes something like this. If I have got a large number of bits, I need all the bits stored in shift registers and added. That does not look very area nice. It will take quite a lot of area to make. Right? We just looked at adder and that was taking a lot of area. There are also people who do array multipliers, but it will remain the same thing. Now, how many of you have been taught the concept of Booth multiplier? 2 people, so you can teach us the Booth multiplier. Come on, tell us what Booth multiplier is. Circular and shift. Okay. So, for the second years who haven't come across Booth multiplier, we will do it very quickly and you guys can close your ears and eyes for some minutes. The multiplier concept comes from very simple. If you have to multiply a number by 10, what do? You just put a 0 at the end. If you want to multiply a number by 100, what do? You put 2 zeros at the end. That's a simple concept. So if you have a series of zeros somewhere, you don't need to actually multiply, you just shift the number. Right? By putting 0, I mean if I have 12, I'm putting 0, I'm just saying I'm just shifting 12 one side and putting a 0 there. Agreed? Now how do you multiply with 99? So multiply the number by 100 and subtract the same number. Okay? So you could do same in binary logic. If you're multiplying a number by 1, 1, you can multiply it by 1, 0, 0 and subtract that number. Okay? The first part is easy. Multiply by, put 2 zeros. Second part is add that number, add the 2's complement of the number. Okay? So one thing which we could do, sorry, we're not going to do this thing here. Remember we are looking with signed bits. Okay, so the first bit is denoting it's a positive number or a negative number. So one thing which we could do is we could look at these factors. We could look at group of numbers. If I have got a long sequence of bits to be multiplied, rather than multiplying it all at one go, I look where there are sequence of zeros or ones. And sequence of zeros, wherever I do, what I do? I just add zeros later. Sequence of ones I have, it means I add zeros and then subtract that number from that. That way I can reduce my computational complexity of multiplication. Okay. There comes the concept of Booth multiplier, which goes by this very simple algorithmic approach. If you get, and we're just looking at 2 bits at a time. Let's start with, we can also, there are also 3-bit Booth multipliers. So if you get pairs of zeros, just shift the number. If you get pairs of 1, still just shift the number. Don't do the subtraction right now, because we will only do subtraction when we get 0 or 1, because that seems that 1, 1, it might be pair of 1, 1 and then there could be another pair of 1, 1 there. Okay. So when you get 1, 0, that's the time you subtract and shift. So you add the 2's complement of a number. When you get 0, 1, you add and shift. So you will get something like this. Okay. Okay, here's another example when we are multiplying 13 by 9. You can just sequentially add and shift, add and shift, add and shift, and in the end you will get a result. Okay. Okay. I'm not going to in details because Booth multiplier is taught in most undergraduate courses. So even those who haven't come across this, you will see that in due course of time. It's also well known if you have a number which is continuously frequently changing 0, 1, 0, 1, 0, 1. Booth multiplier is not a great multiplier because it goes to the worst case scenario. Other thing worth remembering is you don't need to just do 2 bits, you can do a 3-bit sequencing as well. You can do modified, because if you're multiplying with 1, 0, 0, that looks like multiplying the number by 4. Okay. So let's go back and see what we are doing in Booth multiplication. Now what do we need to make a Booth multiplier? We need an adder, right? When we are saying subtract, we are adding the 2's complement. So we need an adder circuit. So a 64-bit adder is needed as well. Okay. I also need something to shift. So if I was multiplying to 8-bit number, I will need a 16-bit shift register because the result will be 16-bit. So I'm multiplying to 64-bit numbers, I will need 128-bit shift register. I need a control logic which looks if it is 0, 0 or 0, 1, something to look at that, a comparative logic. And I need a place to store the number as well as its 2's complement. So if nothing else, I need a 64-bit adder, a 128-bit shift register, and a bit more control logic. 64-bit adder, we counted the number of transistors it needed. 128-bit shift register, how do we make shift registers? By D flip-flops. Anyone remembers how many transistors a D flip-flop needs? Around 15, at least 10, certainly not less than 10. Let's be generous and only give 10 to it. I think it's around 20. Depends upon whether you design using pass gate or you design using. So the bottom line story is we would burn about 3 to 5 billion transistors in making this neural network. We have not yet implemented the training scheme. Remember, in the training scheme we needed to look at the output, take the difference, and then go back and update my input. So even before implementing the training scheme, I have burned a large number of transistors making this neural network. Then the other thing is this memory. What kind of memory can I have? So what kind of memory cells do you guys know? What kind of memory do you have? Be loud, guys. Primary, secondary. Okay. Okay, RAM, I know. What kind of RAMs have you heard? SRAM, DRAM. Okay, good. Well, now we have got noise in the classroom. What are DRAMs? What are they physically? Transistors. Well, transistors are used to access them, but most DRAMs are a capacitor. Right? It's essentially a capacitor which is holding the charge. But DRAMs are not typical capacitors. They are special purpose capacitors. Remember the way we make them. For making capacitors, you need a parallel plate. Right? If you saw the chip early morning, we had loads of parallel plates, but they were not big enough. So to make DRAMs, generally what we do, we drill a trench in the silicon substrate and then fill it with conducting material so that we get a big capacitor. If I get time, do remind me to show you some SEM images of DRAMs. Which means DRAM are actually, even though they are good memory, they take a very small area, it's just a capacitor. They cannot be built in every process. They have specialized process to make DRAMs. Okay, and actually below 14 nanometer process, DRAMs are not really being very successful. So we're using quite a lot of SRAM, yes, but DRAMs not. Now what's an SRAM cell? Have you come across an SRAM cell like this? So it's essentially two inverters back to back. So we have got the output of one inverter connected to the input of one inverter and the output of this connected to the input. So it's basically a inverter which keeps on regenerating its own output, and we have 2 access switches which are there to read or write. So that's for 1 bit. If I have 64 bit reads, I need 64 into 6 of these as well. You can immediately see that is not feasible on a chip. A deep network is very difficult to implement on a chip. A shallow network, yes. A small network, yes. The other problem which we have is we are actually camera designers. We thought we can have a neural network with the camera, and then you can do anything in the real time. Right? Take a picture and tells you what the picture is. But my camera is already taking a large amount of area. We had already a large number of pixels. We have already got a large number of diodes. On top of that, I have to make these. It's very difficult to put them on a chip. So, yes, the industry is doing this quite a lot. There are a lot of people who are working on a digital deep neural network implementation on a chip, and there's a lot of work going on, don't get me wrong. I would like to argue that whatever you do in digital processes, the number of cells needed will still remain large, and hence so many cells will also consume a lot of power. Each of these, we haven't talked about power till now, each of these gates are consuming power. Even though in CMOS we say there is no static power, actually there is due to leakage. Dynamic power will always be there. Okay. So let's now go and see how do we make this neuron in analog technique, and is that actually any beneficial? Because I still have the same problem. I need to add, I need to multiply. So how do I multiply in analog? At the end of the day, I'm going to be very tired because I have to stand the whole day today. How do we multiply 2 digits in analog things? Yes, resistance is a good multiplier. It multiplies 2 things. That's not the only multiplier we have, do we? There are a lot of physical equations which try to multiply 2 quantities. Okay? So he talked about using the Ohm's law, which basically multiplies voltage with conductance. Okay? So in our configuration, we have no configuration, no shortage of such laws which multiply 2 numbers. We can have tons of multipliers. The other beauty is resistive multipliers don't need each bit multiplication. They are doing it all at one go. Right? But we don't like resistors. Few reasons. They're difficult to make, and we are making things small and small and small, and now you will come back and give me a 10 kilo ohm resistor. That will take a bit of area. They're even more difficult to make uniformly, because you're not only asking for 1 multiplier, you're asking for a million multipliers. And the worst of that, they carry current. Current flowing through resistor gives power, I square R. Right? So whatever I do, they will carry the, but they still do a very good job. Now how do we make, so we can possibly use resistors for multipliers. How do we make adders? How do we add to signal in analog? This has been taught even to first year students. Do you remember op-amp based addition? Like 2 resistances, 1 resistor, and that adds 2 signals, right? So remember, when we are doing this voltage based multiplication, we are getting a current output, right? Our output is current, so we need something to multiply, and that we have seen in undergraduate. So if we have tons of current, all of this pass through a op-amp based circuit, we will get adders. Okay. The question then comes is of memories. Not only I need a multiplier and adder, I also need something to store my data. Okay. So when the last time, artificial intelligence have had summers and winters. And by summers and winters, I mean sometimes it has been very popular, the cool thing to do, and then people stopped working on it completely. So it's not a new term which we are using. In 1960s, when computerization started for the first time, people thought, well, we have got an intelligent machine and AI is going to come and take all our jobs. 10 years later, it died. In 1980s, we had things called artificial neural network, ANNs, which were spiking neural networks. And once again, people thought, oh wow, cool, they can solve all these problems. And then they did this thing. 20 years ago, we started with this deep learning convolutional neural network bandwagon, right? Has it started dying already or still going on? How many software engineers did Google and Meta fire in last 2 years? You guys don't read those news, right? You only read how many people got jobs, not how many people lost their jobs. So what happened about 5 years ago? See, industry works like sheeps. So everybody thought AI is the solution to everything. So a lot of engineers were hired. And now all of a sudden you realize either it consumes too much power, it does too much training, there's not enough data. It's good for centralized people like Meta or ChatGPT to come up with something, but not necessarily terribly good for all the simpler problems. So all of a sudden you're not going to have AI based people for doing this thing. The reason why I started talking about history of AI was last time when AI was cool, the way we were making memories were these flash memory drives or EEPROMs. All of you have used them, right? Do you know how they work? Has it been taught to you in your undergraduate? In your graduate studies? No? So the way these devices look like, they look like transistors, but rather than a single gate on top, they also have a floating gate in between. There's a second gate here. This gate is not connected to anything. So same source drain, there's a gate which is not connected, and then there's a top gate which is connected to something else. Okay? The idea is, by using tunneling operation, if I apply a high voltage here, some charge will tunnel through this dielectric and come on this thing. Okay? That charge staying there changes the threshold voltage of the transistor. If I want to remove it, I apply high charge to the body, and this charge comes to the tunnel through hot electron tunneling and then goes away. So that's how you program and discharge a flash gate. You're essentially, in the digital EEPROM devices which you have, it is essentially storing two values of threshold voltage. And if you remember your MOS transistor, you change the threshold voltage, you change the current output. Okay? So the threshold voltage can be used as something to store memory. Now you might ask, why only two values, 0 and 1? We can certainly store many different threshold voltages. Some of those who have done MOS design, what was the typical threshold voltage of your transistor? 0.6, 0.7 volt. So I don't have big headroom to change it dramatically. Right? So a lot of work actually has been reported in literature where people have used these memories to make neural network. But the interesting thing about these memories is the neural network would be this big on the chip. The control logic to control would be this massive right next to it. Because now you need to provide high voltages, right? And you're talking about a 3.3 volt technology, you're talking about 15 or 16 volt to apply. So you need charge pumps to produce that voltages. So brilliantly works, can be used, but cannot be reproduced, cannot be done with a large number of these things. This leaves us within a trouble. We can make multiplier, we can make adder. Our memory solution is not terribly good, particularly analog memory solutions. And this is where some hope lies in new type of memories which are coming up. A lot of it is in the research domain. We are also writing papers on that. Most of these new type of memories are not based on circuits. They're not transistor. Remember, all the memories which we talked till now, they're transistor based. Right? SRAM was transistor based. DRAM had a capacitor, but still transistor based. Flash has got a floating gate, still transistor based. And this is where the problem lies. Virtually every foundry think their memory would be the one which will take the market. Remember, memory market is huge. And the whole reason okay, not whole, but I believe Samsung became such a big company because their memory business started flourishing. Okay. So number of memories which are there, and these are the words you will hear quite a lot. There is phase change memories, who change their phase, and phase could be resistance or optical condition based on applied heat. Okay. There is magnetic memory. In magnetic memory you have things wherein you are using a spin and orbit of magnetons, or the torque in the tunnel. You have resistive memories whose resistance changes by doing something, by applying a voltage or by applying heat or giving energy. Somehow you give the energy to the system. You have ferroelectric memories which are kind of magnetic based. You have oxide replacement memories. You have conductive bridge RAM. And sometimes, like conductive bridge RAMs, many times are similar to RAMs, but because of industrial pull and push, they are all being called different names. So every foundry has got their favorite, or they have got 2 or 3 of their favorite, hoping one of these will succeed in market. So right now in the stage wherein we don't know which one of these will succeed. The other issue is, remember, they're not transistor based, they're physics based, they're device physics based. So how they will scale? Transistors, we know, as we made the transistors smaller, the memory also started becoming smaller. How will these scale is an open question. So we are in that flux where a lot of neural network work is going on based on these new type of memories. We don't know which one will succeed, if any one of them will succeed. Okay. So with that warning that maybe none of them will click, I'll just introduce one of these to you because physically they are beautiful devices. Okay. And that's the devices called memristors. So ignore whatever is written on the circuit. So you knew things regarding voltage, current and charge. You know these 3 things? So the relationship between voltage and current, there's a fundamental material called a fundamental element of electronics engineering called the resistance, which relates between voltage and current. Okay. There is capacitance, which relates between voltage and charge. And of course, between charge and current, you have the time-based relationship. We also have inductance, which basically relates between flux and current. So when we say d phi is L di, now flux was kind of one of the most ignored things when we learn. So we don't talk much about flux in our undergraduate. We know what it is and then very quickly move to L di dt, don't we? So Leon Chua argued that if I put them all in a kind of a rectangular block, I have a relationship between this and this, I have a relationship between this and this, I have a relationship between this and this. So there has to be something which relates charge and flux as well. There has to be the 4th fundamental element. And he predicted it will be a memristor. It will act like a resistor, but it will also have a memory. It will remember its past states. So formulation wise, it's just d phi is equal to m dq. For a long period of time, Chua predicted its existence in 1970. It wasn't seen. It was one of those theory papers which was good to read, but no one had seen this. HP was able to show similar behavior in very thin stacks made of metal oxide. So if you had 2 conducting layer on top and you have metal oxide in between, they saw similar behavior. The beauty of these devices is you apply high voltage, their resistance changes, but the resistance remain that till you apply a very low voltage. Now, we have been trying to make, now the devices work fairly okay, they are still not stable. Nobody has been able to make a million odd memristors. Remember, in order to make a neural networks, we'll at least need a million memristors to put the weights. We are also making them. We can barely make 16 by 16 arrays, small arrays of memristor. The other issue which has happened with memristor is, again, which material do we make of? So typically memristors are formed of 3 stacks. Again, I will bring some pictures tomorrow to you guys. So essentially, the kind of memristors which we make, they have a top active layer, a metal layer, and a bottom layer. In between, we put a dielectric. So otherwise, it looks like a capacitor. Okay. Now, if you take a very thin dielectric, it will have a high resistance. Right? It will have, and all capacitors have a resistance. It just have a fairly, and the layer thickness we are talking of is a few tenths of nanometer. Now, what we have seen, what other people have seen before us, is that if your top layer is made of some metals, so in our case, copper, silver, molybdenum, okay, and the bottom layer is neutral. All it does is provides a contact. It doesn't do anything. So we can make platinum or ito or any metal you want. So if you have a thin, say, dielectric, something like silicon dioxide or amorphous silicon, and you have a thick layer here, you apply a certain voltage. What happens is these ions start moving in this dielectric. Okay, do I have a, oh, this is tied here, I can't remove it, but okay. So as ions start moving in, so you have copper on top, and copper ions are slowly moving into the dielectric. If you keep on applying high voltage, at some point they go and touch the bottom electrode. Now, as you can see, what has happened is I have formed a channel of copper ions. Copper ions channel will have low resistance. So something which had high resistance, by applying a voltage, it has now resulted in low. Even when I remove the voltage, these ions will not travel back on their own, because this is a solid structure, right? So ions will not travel back. Now I have got a low resistance state. The only way to remove the ions will be to apply a high voltage to the bottom layer and negative voltage to top layer, so that all the ions get attracted back. Okay? So this gives us 2 resistive states. Now, by applying high voltage, I mean 1 or 2 volt we are talking about. Right? So 1 or 2 volt of positive voltage forms the channel, 1 or 2 volt of negative voltage removes channel. And I will show you some examples in one of our later lectures. Now, the reason why this device is interesting, it is a resistance. For when I'm not charging, when I'm not applying high voltage of 1 or 2 volt, if I'm applying 0.5 volt, it is a resistance. Okay? Which means it's a multiplier. Okay? The other thing is, I can change its resistance value. So when I'm programming it, I can apply a high volt and shift its resistance. The people have also tried doing pulse and giving many resistance values rather than just a low resistance and a high resistance. You can have multiple resistance states in between, which means we can make something like these crossbar arrays, wherein, say that's my input signal V1 to so on. These can be multiplied with this memristor, plus it's the same current. So current in series gets added. This can be multiplied, current in parallel gets multiplied with this resistor, this can be, and then we can feed this to a summing amplifier at the end. So and rather than designing each neuron, we just create these large arrays of memristor and then go and program each, because in a neural network, the same input will be fed to many different neurons. So that way you have got, if that is the output of one neuron, this is to the second neuron. So conceptually, they are very nice devices. They appear to be potentially the future of neural network design, and if we can make them, if we can stabilize them, the problem with these devices is they are not stable. They still take programming. You still need a programming circuit to put high voltage or low voltage to make them work. There is massive variability in these. every 2 memristor behaves very differently, and order to stabilize are still up in progress. So people like TSMC are trying to do it, but it's still very early stage. The problem of power consumption is still not very solved. They say these are consuming less power than our equivalent of digital logic, but the moment I use resistance, current will flow through resistance, right? And we will have power dissipation going on. So the only way to reduce that, because remember what we are doing, we are applying voltage across a resistance. So voltage is my input. So how do I reduce the power dissipation when I apply a voltage across a resistance? I can either reduce my voltage or I can increase my resistance. So V square by R. So if I can make, the problem which I have is the moment I make the bridge, I get a very small resistance. Okay. So the trick the research direction which people are taking now is how do we increase the dynamic range of these resistors, how do we change the resistances so that we get lower power. So conclusion for the first 45-minute order of the lecture is that the classical von Neumann computer which you have been using for so long makes very cheap and powerful machines. You all have a von Neumann machine with you. But they are not the ideal machines to implement neural network or artificial intelligence circuit. We can make a neural network out of digital circuitry which is available to us. Analog seems to do better job at this point of time, or at least looks to be doing better job at this point of time. It still has got all the issues of noise, variability, reproducibility, and those are still very high research topics for us to play with. But it is promising that if you're going down the direction of machine learning or neural network based systems, we might have to revisit the entire digital design the way we do it, or else power is going to be a big concern. Or else what might happen is we never go to, so you know how we went from large machine to personal machines. If we don't solve that problem, we will never have personal neural networks. So that is a research direction where a lot of work is going on right now. We don't have any solution yet. So we'll take a break now, and when we come back from the break, we have done 2 or 3 things today. We have looked at lumped parameter models in the morning. We have looked at neural networks. So why don't we do some exercise problems? So in the second half, we will do some tutorials. Okay. I will come around and help you guys. We'll set the problems on the board, and then we'll do the tutorials. Because if I do another lecture, you guys will be dead. Right? There's only so much lecture we can hear in a day from a same person, and there's only so much lecturing I can do. I mean, I can talk another hour, but my brain is already dead an hour ago. And it's a day for fasting for me. It's Purnamashi, so I haven't ate anything. But so I think it's better we do some tutorials. Tomorrow morning, I have been told the lab will be available, so we'll be now. Okay, before I let you go, so there are 2 things which we should have discussed about. One is neural network designed and trained, but there's another approach which is happening in research. Why do we need to constantly learn? So if a neural network has been trained in cloud or trained in data center, can't we just physically make that trained neural network with those parameters? Okay. If we have to do that, then we don't have to learn. We don't have to change the resistance. We just build finite resistances in the chip. Okay. How can we make resistances in the chip? So one is memristor. Say our process does not have memristor. What other ways we can make a resistor? We can make a long wire, that's a resistor. It's a small resistance. Or we can use a transistor. Remember, transistor operation goes up and then flat lines. The time it is going up, it looks like a resistor. It is a resistor. It's a voltage dependent resistor based on the gate voltage, and I can change its resistance slightly by applying different gate voltages. Okay, so we can use a transistor as a resistor. So one thing which we could try doing tomorrow, those who haven't done the image sensor, it will be a good idea if you guys go and do your pixels. Those who have done the schematic of the pixel, I will sit with you and we will do the layout, because layout is fun. And if you reach even that stage, then we'll try to make a perceptron, a simple neuron using purely transistor, no memristor, nothing else. Okay? Good. Let's take a quick break now. Country is Bihar. It gave me the boundaries of Bihar. So if I now ask in which country is Assam, it should give me the boundary of Assam to be Arunachal Pradesh. It seems as if like somebody had just gone to the head office and asked, what should I reply to this question? Let's try that question again. In which country is Assam? Okay, ChatGPT gives a decent explanation of McMahon line. Should we ask the same thing to DeepSeek? DeepSeek has figured out, don't try this guy. Let's ask anyway. What do you think would be the reply? Server is busy again. It will chicken out. Ah, come on, it's so fun to make fool of AI. And we had this, I was doing a Viva a few days ago, and we asked a question. Is it because we are based in India? Should we try me being based in Germany? Problem is, how can I blame even NIT network doesn't allow you to go to many web pages. I can't even do VPN to my own. There's this VPN banned here. Really? Why? It is on. It's not on. Not on yet. I can hear myself. Okay. So this would have been a much easier circuit to simulate. Okay, let's do the reverse. Let's do the reverse for a change. That's my electrical circuit. Convert it into its mechanical counterpart. And electronics engineers are going, if it's already in electrical world, why going back? What is this? Oh, the electrical equivalent. May I just? So this is the thing with mechanical forces. You need something to move from, right? Yeah, good. There's still scope in Deutsche Bank. Oh, you have put this thingy as well. Good. It's not, but there is no equation here which shows how it is moving to the ground, right? So it looks nice, but yep. So this is relatively easy. Most of you have got it. Well done. Okay, so a number of you would have got something like this. Okay, stiffness to mass, and then stiffness and a damper to another mass. Good. Before I start doing something more serious, or one more problem, why don't we take this perceptron? Let's just assume it has got two inputs and known outputs. Can you guys train it? Remember what we did in training? We basically said that for the given set of inputs P1, that's my expected output. For P2, that's my expected output. Okay? So it's a two input system, it will have two weights. I need to find the weights and biases B. So start with weights being random. So there are two numbers, you can only pick 0, 1, 0.5, 1.5 something, and then see if it converges. So any luck? I'll just break for a second and then I'll bring it back again here. Okay, while we do this, let's do some quiz type questions. Okay. Uh, what makes a neural network deep? Again, can I hear?
Hidden layers.
Layers in plural. Wrong answer.
Connectivity of more
Nana. Look at my word which I said. Layers in plural. A single layer is enough to make it. Okay. Why are MEMS? Oh, you guys were not there at MEMS census, right? Now, one at a time, can people give me some example of activation function? What is the kind of activation function we have used today? Sorry? We used a hard limiter, right? It was a hard limit. We used a simple function below other. Anything else you guys have? What are the functions? We saw functions which look like this. So what will be the mathematical counterparts of these? Tan H, hyperbolic tan, right? Sigmoid, what else? Ramp in a good day, yes. There are also functions like ReLU, which some of you might have come across, rectified linear units. Okay. Now, I know we have limited time, so on the same folder where we tried putting our images the other day, what I have now done is, and I'd rather do it, just give me a second. Okay, so you will be getting most of my lecture slides as printout, but on the same folder I have also placed a collection of book for you guys. Okay, now because the network is slow, I will just show you what is there in the book. The book contains, it's a 130 odd page book. You don't have to read all of this, but I have given two book chapters which are the fixed pattern noise is my article in the Encyclopedia of Optical Engineering, and then there's another book chapter on CMOS sensors for wide dynamic range imaging. Okay, if I will also put another book chapter which we wrote on advances on digital imaging. Okay, so it covers the whole theory which we have discussed in more details in case you are interested in further studying. After that, I've put some review articles There's one review article on temperature sensor. I know we have not covered temperature sensors till now, but we will cover this before I go away. This basically, it's a very good article which covers, oh sorry, there's only one page. Okay, I'll put all of it articles soon. And there's also a review article on microbolometer type infrared detectors. So temperature sensors can come as waveform detectors as well as heat detectors. We'll have a look on these. And then there is an article on chemical sensors, primarily pH. Ooh, that's where the second part of temperature sensor is. Okay. So it talks about various circuitries which are used in temperature sensor as well as the type of sensors to be built there. There is one tutorial article on ISFET arrays. These are the ones which can be used for measuring pH in solution. Okay. So I will be discussing the theory in the classroom, but it's only a 2-hour theory discussion anyway. So this entire book will be there for you to download, keep it for free, and do whatever you want after that. Okay. So that will be available for free for you guys, and of course all the lecture slides and everything is available as well. The books do have copyright, and so have the articles. I'm giving them just as educational material. They should not be used commercially. I guess you already know the rules of regulations. Please also don't plagiarize things from there. If you want to use it, just cite the book and that will be perfectly fine. Okay. I will also be putting all these tutorials. I have the many number of other questions which we have. So part of this course is helping me draft a book on microelectronic sensors, as I said in the beginning. So each one of these sessions is becoming part of my manuscript. I also did another Gian course in Rourkela where we are writing a book on financial engineering, so application of engineering in finance. So I'm hoping someday I will have enough energy to finish both of my books and then I will go to sleep. Good, it's almost 5 o'clock. I know we were a bit slow in tutorials, but then that's what happens when we are working on it. We will stop now and we will join again tomorrow at the same time at 9:30. And for those of you who are interested, so what am I planning to do tomorrow? Let me just have a quick look. So tomorrow we will cover temperature sensor, infrared sensors and temperature sensors. Okay. Part of this is, so infrared sensors are one of the strangest creatures. They have been built from Second World War onwards. They're also the ones which the defense industry demands the most and restricts the most. So I will not be able to talk to you everything about infrared sensor. Remember, I come from Europe where I have got export control restrictions on what I can tell you. But we will tell you normal coverage, particularly in most normal applications. But as they are used to find heat, and there are things like heat-seeking missiles or heat-seeking geolocation, much of this is restricted. Even though there is a lot of application in biomedical world. So people got accustomed to infrared sensors during COVID times when you had remote temperature measurement. So we'll look into how these sensors are made, what is done. We'll again be doing a cursory tour. We'll not go as deep as we went to camera pixels. So in the second half of the day we will do that. In the first half of the day we will do the labs. Okay? Any questions? If not, have fun. It's Wednesday. What's the worst could happen today?